Now let's look at how efficient coding can help us to understand the forms of neural resistive fields. We will show a formulation of the problem and a general solution for the optimal resistive field when certain conditions are satisfied. Let's first review and set up the notations. Let S plus N be the receptor responses to visual inputs. They are both vectors, S and S is for the signal and N is for the noise. The responses of the downstream neurons are O, so O is a vector. The resistive fields are approximated as linear, so encoding K is a matrix with matrix elements Kij. Okay, and NO is the additional encoding noise. It's also a vector. And OI is the response from the downstream neuron I, the I's neuron. And SJ is the J's input component. For example, it could be from a spatial location xj. For example, you may have 5 input nodes, S1, S2, S3, S4, and S5. In that case, and the Kij then describes this I's neurons' neural resistive field properties or input feature properties. So if input S is for spatial inputs, then K describes the neuron's spatial resistive field. For example, if you have an output neuron OI, then Ki1 is the effective connection from S1 to OI, and then Ki2 from S2 to OI, and so on and so forth. And all these neural connections, the effective neural connections, then describes the resistive field for OI. And of course, if you have another neuron, then it will have another resistive field. So different rows of K will describe different resistive fields for different output neurons OI. And Sj can also describe input at time instant Tj. In such a case, then the encoding transform K describes the neuron's temporal resistive field, and we can use this to get a neuron's temporal response function. Sj can also describe visual inputs from different cones, so different J's for different cones. Then Kij then describes a neuron's color selectivity and color tuning. And so also Sj can describe inputs from different eyes, so for stereo vision, binocular vision. So for instance, J equal to 1 for left eye and J equal to 2 for the right eye. And then Kij will describe a neuron's ocular dominance properties. And Sj can also describe inputs combining all these input feature dimensions. So for instance, Sj can be a particular space-time conjunction or space-color conjunction, etc. And so in such a case, then Kij is a neuron's conjunctive feature tuning, for example, for a neuron's spatial temporal resistive field that's combining space and time, so you can describe the motion tuning properties of the neurons, or a neuron's spatial temporal, spatial chromatic tuning. So in all these cases, this general formulation can apply. And so let's first derive the general solution K without specifying which input feature dimension we're referring to. And then we can apply the solution in various examples, specific example, to get more concrete results, and then to understand our neural data and see if this makes sense. For simplicity, we also assume that all the signals and noises have zero means, and so that can make lots of notations and derivations a bit easier. If they do not have zero means, we can always do some translations of our coordinate system so that we can make this is the case to simplify things. So we need to find the optimal matrix K to minimize this objective function Ek. To do that, we need to first have the probability distribution of our input signal, Ps. Okay. For a vector S with many components, this means to get a joint probability distribution on many dimensions. And this is not easy, particularly when n is very large. For example, when n is the number of image pixels. Yeah. However, we can more easily get another statistical property of the input signal. And this is its second order correlation matrix. Okay. And so this matrix is denoted as Rs. Okay. And it has this Ij's matrix element, and Ij's matrix element is a second order correlation between the Si node and Sj node of the input. Okay, and you can see that this is correlation is Si Sj, and it's averaged over by the probability, joint probability Si Sj, and integrate over Si and Sj. Okay, and this is much easier for us to get as properties of natural inputs. And with this correlation matrix Rs, we can then approximately write the probability distribution as if it's approximated by a Gaussian. Okay, in this Gaussian, you can see that Rs is still the matrix Rs, and now it's taken inverse, and for its after it's taken, it has the Ij's element, and it's added together by the summation Ij, Si, Sj. And so this is a Gaussian approximation, Gaussian distribution of a whole vector S. Okay, and this may look a bit complex, but we can see the special form when S is not a huge vector, but just a scalar. This is a familiar Gaussian distribution we are familiar with. Yeah, and in this you see this quadratic S squared. In this is now replaced by quadratic term Si times Sj, and the variance of the S in this form, sigma Si, is now replaced by correlation matrix. So a number variance is by correlation matrix, yeah, and then of course you have to sum over Ij. So this is complex, this is familiar, but we can get a feeling that this is a Gaussian approximation. We will later show that this Gaussian approximation is not bad. It quite reasonably describes the statistics of natural inputs in many situations. Also, Gaussian approximation makes it easier for us to get analytical solution for the K-matrix later. Thirdly, this Gaussian approximation captures our ignorance about the true probability distribution, the joint probability distribution. Since it turns out that this distribution not only gives us the second order correlation correctly as data, but it's also the distribution with the largest entropy while keeping the second order correlation fixed. In addition, we also assume that all the noises are also Gaussian, although different components of the noises are independent of each other. Okay, that makes it even simpler. Additionally, we impose this quadratic form as the neural cost. It can be seen as the total energy at the output, or the total output dynamic range. And this form also helps to get the analytical solution for the encoding matrix K. That's the optimal encoding matrix K, which we can get by solving this equation. This minimizes Ek. Okay, we're going to omit the details of the derivations, but in the end, the solution K that minimizes Ek really comes out as a multiplication of three special matrices. The first one is the matrix Ko, and this matrix Ko is to diagonalize the input signal correlation matrix, so it does the principal component decomposition on the input signals. So this matrix is completely determined by the correlations between the input signals. Second is a diagonal matrix G. It gives a gain control to each of the principal components. Third is an orthonormal or unitary matrix. It's for multiplexing the gain-controlled principal components. So it's like another coordinate transform, and we have the freedom to choose what this coordinate transformation is. So therefore, the optimal K is dictated by an optimal diagonal matrix G. And so let me show you a little more intuition what all these means. The optimal transform K does the following conceptual steps of signal processing. From the input signals S, first it transforms the signals to their principal components. So these components are then independent of each other. Then for each principal component, it gives a gain control by multiplying each component by this gain GK. This GK is the diagonal elements of the diagonal matrix G. The GK values are given by this complex looking formula, which I'll explain later. And the outcome is then this OK for each component K. Note that this GK value are completely determined by the signal to noise in each principal component. Okay. Finally, these OK for different Ks are mixed together by the U matrix to give the final neural output signal OI. Looking at the GK, or rather GK squared, in more detail, this plot gives the GK square value versus the signal to noise of the principal components. So the horizontal axis is for signal to noise, and it decreases rather than increases along the axis. This is in order to follow the order of principal components, which is ordered from components with higher signals to those with lower signals. And the vertical axis is for this GK squared. We can see that this GK squared is composed of two factors mainly. One is here, and we call it F smoothing, and the other is there, and we call it F decorrelation. When the signal to noise is high, this F smoothing, this is the red curve, and when the signal is high, F smoothing is a constant because, when this term is almost negligible, so it's a constant. But then as signal noise becomes weaker, F smoothing cuts down. So this F smoothing factor does signal smoothing, or to smooth out the noise, by cutting out weak channels which are dominated by noise. And for F decorrelation, it follows this blue curve. It's actually does the opposite. Okay, as the signal get weaker, it increases, because it does the decorrelation. Since the small principal components represent less correlated input signals. So as a result, the GK value follows this black curve. So as the signal noise is high, it's dominated by decorrelation because F smoothing is constant, it follows decorrelation. And as the signal noise become weaker, it starts to go smoothing because it gets cut down by that. So these two factors put together gets cutting down. And so therefore we see that this solution optimal encoding has this decorrelation and smoothing coming out, emerges as the solution rather than two separate strategies. It's just two separate regions of signal noise. And there is a sweet spot where you have peak sensitivity to input signals. Because this coordinate transform U can take many different forms, many different solutions of K, which is composed of K0, G, and U, are equivalent for the optimal solution K to make EK minimized. But this choice for choosing different U can be used to satisfy additional constraints or needs that have not been specified by EK. Secondly, I also like to point out that these three conceptual steps, okay, so K0, G, and U as in these three boxes, okay, they are only conceptual. The actual neural implementation for the same K matrix, okay, just one K matrix is enough. Of course, you can also have a cascade of many multiplication of many matrices as long as the final K matrix is fixed by this, okay. And they may take different actual forms of implementation due to hardware constraints, perhaps also due to needs for adaptation when input statistics change. This K has to change. Okay. Now, in the rest of the course and the book, in the rest of the chapter rather, we are going to practice using this K transform in many concrete examples of neural-resistive fields and see how we can understand them as optimal encoding transform. Okay, there will be resistive fields in space, time, color, or combination of them, or chromatic, stereo coding, etc. So we will have many chances to digest these materials and these concepts.